Dear students, so this is the first video for our subject 22 CE C61 Structural Analysis 2. Structural Analysis 2. So, as same as the Structural Analysis 1, here we are going to analyze the determinate as well as indeterminate structures with different methodologies. So first two units concentrating on influence lines diagram and calculation of shear force and bending moment values and other the stress resultant. Third and fourth unit concentrating on the same calculation of the shear force and bending moment for arch, cable and suspension cable. Fifth unit concentrating on the analysis, same analysis to find out the bending moment, ultimate bending moment or the collapse force for the plastic analysis. So in structural analysis subject, we are concentrating on the calculation of shear force and bending moment. So this is very much familiar to you from your third semester onwards. So there will be no difficulty in calculating shear force and bending moment. I hope so. In this, we are going some deep into the subject that I think you are able to understand clear for a simply supported beam loaded with a point load having the distance of x from the left support and the L minus x from the right support so that the total length is L and keeping the support name A and B. So let us calculate the RA, RB value. So RA taking moment about A equal to 0 will give the RB value. So RB into L minus W into X equal to 0. That is, you have to rotate all the forces about A. So this force will rotate like this. RB reaction and the total load W is rotating in the opposite direction. So while making the statement MA equal to 0, we will get RB into L minus W into X equal to 0. I am giving plus and opposite sign to W, but by using the sign convention, you can relate. Consider a cutting section. So this force will rotate in a clockwise direction. So we always make it as a positive sign convention. And the opposite direction will make an anti-clockwise direction. So the sign convention used there is negative. So if you cut at this point, RB is right side upward. So the right side upward is considered to be minus. So I can write this equation instead of RB is positive minus RB into L plus W into X equal to 0. Both are same. Both are same. When you equate this equation into 0, both are same. So in this equation, I am following the sign convention. Here I am oppositely following the convention, but both the results will be 0. While you calculate here, it is Wx by L. While you calculate here, the same answer you will get, which is Wx by L. Where based on our sign convention, RB is negative. That is negative shear force. RB is negative shear force because of while taking a cutting section inside the span, right side upward is the direction of RB. So we are following right side downward is positive. So RB is opposite to the considered direction, positive direction. So we are making RB is negative shear force. So this is very one important point in moving load. RB is always referred to as negative shear force, while RA is referred to as positive shear force. Okay. Then we have calculated RB value. Okay. We can refer it as a minus value. How to calculate RA? RA equal to total load minus RB. So total load here is W minus RB equal to Wx by L. You take W as common, 1 minus x by L. So W into L minus x by L is the RA value. W into L minus x by L. So if you want to draw the shear force diagram, so RA is here, the direction is left side of the section because our section will be inside the span. So RA is left side upward. So it is positive. So I am going to draw W into L minus x by L is in positive and it will extend up to W. If you deduct W, L minus W W into L minus x by L minus W. So we can expand W into L by L minus W into x by L minus W, so that L cancel, W minus x by L minus W, so we can cancel W. So how you will get minus x by Wx by L. So this is the value which is equal to Rb, because the negative sign indicates it should be in below the axis. So if you deduct W L minus x by L minus W, because here there is a load of W for the ordinate of W. If you deduct W L minus x minus W, you will get the Rb value in negative ordinate, that is W x by L. So this is RA, this is RB when the load is placed somewhere in between the span, which is x distance from the lip support. So this is a prerequisite for this subject. You have to understand very basic things, because in the next page we can see, you consider that is case 1. You consider it is case 1. Case 2, here it is A support, B support. The load is placed directly on the support A. The W is placed directly on the support A and the span is A. Now, what is the RA value? Directly we can say the load is directly located on A, so W is directly transferred to A. By understanding, we can say like this, and or by taking moment about A, you can take moment about A equal to 0. So RB into L minus, there is no load in this span, and W is also located on A, so there is no perpendicular distance to multiply, so equal to 0, so RB equal to 0. So then RA equal to total load minus RB. So total load is W minus RB equal to 0. So RA is directly W. You can see the loading condition and the support condition. You can come to a conclusion that the load is directly transferred to E. So RA is W kilonewton. When you draw the shear force diagram for this case, I can mark W like this, RA, and RB is 0. So you can connect like this. Okay. So this is the shear force diagram for this loading condition. Next case, you place the load directly on B, W kilonewton, and consider two support conditions with the span L. This is A and this is B. From this understanding, we can directly mention as RB equal to W. RB equal to W. In previous case, I have stated that RB is the negative shear Because if you consider a section, it is always upward, so it is negative. So minus W and RA equal to 0. While you're taking moment about B, RA into L, and there is no load in the span, so RA equal to 0. RB equal to the total load, and also the direction of RB is a right side. So right side down is positive, but RB is on upward side, so it is minus W kilonewton. In this case, if you draw the shear force diagram, so RB is W, RA equal to 0. So this is the SFT. Okay. Sorry, actually this is in negative ordinate because RB is minus W. RB is minus W. So the W should be marked downward. So this is the shear force diagram. Because it is a negative diagram, here it is a positive diagram. And this is the case when the load is located at A. This is the case when the load is located at B. Okay. Initially, when the load is at A, the positive shear force is maximum at A and it decreases further and meet the zero value at B. When the load is at or over the support B, the negative shear force will be the maximum and it reduces and approaches zero at A. Here, the positive maximum shear force will be obtained at A due to the load located at A. Here, the maximum negative shear force will be obtained at B due to the load placed at B. So, when a load is moving from left to right, the possibility is the first position of the load will be at A, then only it can approach towards B. So, we can come to a conclusion that initially the positive shear force will be maximum. Initially, the positive shear force will be maximum. The negative shear force will be very much minimum. I can draw a section. When you place the load here, the load is started moving from left side. So initially the maximum positive shear force will be as this ordinate. But because of the travel of the load, the positive shear will be reduced at this level and the maximum positive shear force will be like this. But at the same time, when the load passes from the point A, the negative shear force will be increased. The negative ordinate will be increased for some extent and it will have some magnitude when the load is located at the section because it should be in equilibrium. When the maximum positive shear will be like this and the maximum negative shear will be like this. If you cut a point here at distance x when the load is located here, the shaded portion will be the shear force variation. Because when the load is placed at A, we can have a maximum positive shear force here. But at the instant the load moves towards right side, the positive shear will be reduced linearly. And at the same time, the negative shear force will be increased in the linear manner. So, the shear force variation when a point load is moving is like this. When a shear force is moving from left to right, When a point load is moving from left to right, the shear force variation is like this. So you have to clearly understand that this is two diagram, that is maximum positive shear force diagram. Here it is maximum negative shear force diagram. So in this diagram, the load is located at B support. In this diagram, the load is probably located at A. If the load moves from left to right, I am considering the load position here, then the shaded position, shaded area is the shear force variation, because the positive shear is reduced from here to here. At the same time, the negative shear will be increased from 0 to this value. So this is the shear force variation. And what is the value of shear force? We already derived the shear force value at the x-axis when W is located at x distance from the left, because our reference axis is considered to be A. In this case also, the load is considered to be moving from left to right. So I am considered distance x is from A. So the RA value is, what is the RA value from our previous derivation? W into L minus x by L, and RB value is W into x by L. So we can mention here, it is a negative diagram, it is a positive diagram, because the positive shear will be reduced and the negative shear will be increased. So the negative shear ordinate is x by L into W. The positive shear ordinate is W into L minus x by L, because this is the RA value. Here it is RB value. When the load is at a particular section in the midway, actually the exact section we can draw. So this is the beam, the shear force diagram for the particular loading. W is acting here. We can draw the shear force variation like this. So the negative ordinate is x by L into W, and positive ordinate is the RA value, W into L minus x by L. Here very important conclusion we are going to obtain, that is, here I am making W equal to 1 kilonewton for my convenience. W equal to 1 kilonewton for my convenience. Then the shear force diagram will be, instead of W, you consider 1. So it is x by L. Here it is L minus x by L. This is negative diagram. This is positive diagram as discussed earlier. So this is RB value. Here it is RA value. This particular diagram is called influence line diagram. Influence line diagram. So what is influence line? So it is an influence parameter for a given loading at a given section, representing shear force variation as well as bending moment variation. I have taught you only for the shear force variation. We can later study the bending moment variation also. So the shear force variation, we have taken away W, which is equal to 1, so that it becomes x by L and L minus x by L. What is x by L? Which is RB value from the previous derivation, RA value L minus x by L. So this is the ILD for shear force variation. Then how we can get real shear force value while analyzing a structure? So because we are analyzing with the conventional method W, we can get RA equal to W L minus X by L and RB equal to W X by L. So here the W is multiplied and we can get the exact reaction value RA and RB. But in influence line diagram, here the RA equal to only L minus X by L and the RB equal to representing minus x by L. We didn't get the exact value because there is no load considered, because it is W equal to 1 kilonewton. Then how we can get the final value means, the final value of shear force equal to ILD ordinate into load. So this is a universal format. You have to remember that the shear force value or bending moment value, anything if you want, that is ILD ordinate. Ordinate means vertical distance. ILD ordinate into the particular load. And if you want RA value here, you can calculate x by L minus x by L only with the geometric property, because you kindly note that x is a distance, L is a distance, L minus x and L are all are the geometric properties. You can draw the influence line diagram without any loading. That is many advantages of this method. You can draw the variation of shear force or variation of the bending moment only with the available span and distance, section distances. And you can superimpose or consider the load at this point. And if you want RA value means the ILD ordinates of RA is from here to here, because it is a positive diagram indicating RA. So if you want RA means the ordinate I'm going to this O, A, B. If it is C and D means the ordinate of RA is O into C into the load W. You can find the L minus x by L with the available spans. You can get some value OC into the load will give the RA value. Similarly, RB equal to RB is the negative diagram. So the ordinate OD into the loading W. So this is the basic concept. This ordinate into load applies only when the point load on the span. When the point load is acting on the span, we can draw the shear force variation like this, and we can represent the ordinate x by L, L minus x by L, and we can superimpose the load whenever we want, and we can multiply W into L minus x by L to get RA and W into x by L to get RB. When you apply a UDL over the span, when you apply a UDL over the span, and if you get some shear force variation like this, you have to superimpose the loading diagram over the shear force variation, so that this portion will lie on the negative diagram, this portion will lie on the positive diagram, and you mark the underlying area of RB, here underlying area of RA. So this area will be a trapezoidal variation. Here also you get some trapezoidal variation. So you mark this is A, this is B, and you consider the span as H. So H by 2 into A plus 2A plus B is the area of the trapezoidal. So the area underlying the load is considered to be the total shear force, negative shear force value in this area. Actually, this is A plus B. Actually, this is A plus B. So in this diagram, the shear force is the main factor which influences under the loading. So we keep this is H and this vertical ordinate as the A plus B. And if you consider this, you keep this is H, here it is A, this is B. So A plus B into H by 2 is the positive shear force. Here this area is the negative shear force when a UDL is located at a section X from A. So you will be given a section, you will given a position where you have to find a negative shear force or positive shear force. So then you draw a section and draw the influence line and superimpose the loading there to find the shear force value. So this is a basic concept. We are not at all going into the problem now. So I am teaching you how to understand the shear force variation. Okay. When now I think the influence line concept is only based on the geometric. For example, we consider the span of 10 meter and the section is 4 meter. The remaining span is 6 meter and I am taking the load is 10 kilonewton. I am not placing the load in the span of the beam because it is a moving load. So we have to consider the load is moving from left to right side. We don't know where we have to place. Only the sectional details given in the problem, then only we can place the load. So that I am hanging the load here 10 kilonewton. Here I am giving the sectional details. So find the negative shear force and the positive shear force at a section 4 meter from the left side, 4 meter from the left side. So this is the problem statement. So that I am marking 4 meter here, remaining 6 meter here. So first of all, we have to draw the shear force variation at a section. At a section means there is no uh, different diagram. There is only one different diagram for the shear force variation is like this. Okay. Here it is 4 meter, the remaining distance 6 meter. With the available distances, we can calculate x by L and the L minus x by L. So what is x? X always should be from A because the load is traveling from left to right. So the sectional details should be or x distance should be from A. If your problem given with the some sectional details from B, we have to make the distance from A because if you travel or if you move the load from left to right, then the x distance from A. X distance should be from A. Even your problem mentions some the sectional distance from B, you have to convert x from A. So here x is equal to 4 divided by 10 and L minus 6 is equal to obviously 6 by 10. Then the negative shear force diagram x by L which is equal to 4 by 10. The positive shear force diagram L minus x by L which is equal to 6 by 10. So the revised diagram I am going to draw which is 4 by 10 and 6 by 10. If you add up this both the ordinates, you will get 1 kilonewton because the basic idea of ILD is applying a unit load at the section. The basic idea of the influence line diagram considered to be 1 kilonewton load. So if you add these ordinates, you should get equal to 1. So this is negative diagram, this is positive diagram. Now I am going to calculate shear force and also we have to represent negative shear force RB at 4 meter from left side which is equal to ILD ordinate, negative ordinate at this section is 4 by 10 minus 4 by 10 that is ordinate into the load, ordinate into the load. What is the load given? 10 kilometer. So 10 kilometer. Okay, minus 4 kilometer. Similarly, positive shear force RB at a 4 meter from the left support equal to 6 by 10 into 10 equal to 6 kilonewton. Equal to 6 kilonewton. If you are asking with positive shear force, you should calculate only positive shear force. If you are asking only for negative shear force, your result should be in the statement of negative shear force. Okay, this is very simple supported beam with the point load. This I'm concluding this video. You can extend to the next topics. This is very basic thing of how to understand. Okay.